Okay, so here's what we were talking about last time. Welcome back from spring break. I hope everybody had a nice, relaxing time. Hope everybody squeezed in at least a little bit of math study. Don't forget we have an exam Wednesday. Anyway, here we go. So last time we were talking about what would it mean to do an integral on a surface. I like to talk at the same time about what would it mean to do an integral on a curve. So altogether, here's the kind of questions we want to talk about. Suppose that your domain for your integral is what I might call dimensionally out of place, right? So like one-dimensional domain in a two-dimensional world, etc. And the big idea is really that we want to take the same point of view of chop it up, add it up, right? If we want to compute the mass on a curve, like a bent piece of wire or something like that, the big picture strategy is the same as it was in all of our previous contexts. We have a hard problem of a non-constant density, but I still want to think of mass as being density times size, but the density is not constant. So chop it up into little pieces. Look at the question on each little piece. On each little piece, where you know the size and where the density is approximately constant, mass is density times size. It really is, on the little pieces. So chop up the domain to make a bunch of easy questions, and then add up the answers to those easy questions, right? Chop it up, add it up. So different kind of a Riemann sum, really. Therefore, correspondingly, a different notation for a line integral, for a surface integral. But morally, the same basic idea. Okay, computational strategy. Again, we're going to do pullbacks, and we've walked through the details, a lot of the details anyway, for an integral on a curve. If you have a curve, and if you don't like that as a domain, which we don't, right? Because, it's all curvy and it's dimensionally out of place. It's a highly undesirable domain. Let's find some other domain that we do like, and a function that makes our original curve the image of our new preferred pullback domain, right? And so this pullback strategy we want to do, and we make the observation that, hey, we've already constructed this sort of a function, a function that views a curve as an image, and that is that we're talking about parameterizing the curve. We know how to parameterize curves. We've done a bunch of examples anyway. Okay, so with that realization, we then notice that the little piece of curve that we're interested in, blown up large, that piece of curve I can view as being understood by this vector. Our position differential vector, we talked about the dx vector back in chapter 12, a long time ago. It's just our linear approximation of change in position from, when we were here, based on our velocity and what was happening on the curve at that point. The estimate is that I would end up being over here at some dt time later, and of course we weren't that far off. The actual curve ends up over here. So again, linear approximation. This dx vector can be understood by its coordinates. It's got an x-coordinate, which is understood with partial derivative, with derivatives in this case. And it's got a y-coordinate, also can be understood by derivatives. So the vector I'm really trying to understand, the vector that's going to help me understand that piece of curve, that's going to help me do my pullback, and thus eventually my line integral, that vector is computed just, one coordinate at a time through simple formulas like we just wrote down. Okay. We're going to take the same approach. Oh, and then, plug in, it's that spike the football here, right? So, once you know what that dx vector is, then the magnitude is the ds, and then find the corresponding stretching factor. Okay, and that's where we left off, other than I made a vague reference if we're going to do an analogous thing in the surface setting. So we're going to say this surface that is our domain, that maybe I want to compute the mass of, maybe, right? Or maybe there's a bunch of ants crawling around on this thing, and I want to compute the total number of ants given the population density of ants, or something, right? Who knows? If I can view that as the image of some function the image through some function of a more desirable domain, then I can talk about doing an analogous kind of pullback. So extending the analogy, we call this a parametric surface. Right, so the surface combined with the function whose image it is, we call a parametric surface. And the function is called the parameterization. Okay, we have not done these before, like we had parametric curves. So how to find a parameterization of a surface? We're going to have to talk about that. And there's much to say. We're going to say some now and some later, as in a few weeks. But for now, I'm going to show, after we get a little bit more work done, I am going to show you, one technique that is surprisingly effective for parameterizing surfaces. For now, let's just assume we have the parameterization, and we'll fill in that blank later on. What I want to talk about now is the whole stretching factor business. So just like we did with the curve, there's some little piece of area on our target that's the image of some little piece of area over here in the pullback domain, and I want to know how much does this function stretch out that little blue piece of area to turn it into that green piece of area. Right? And the problem is that this little green piece of area is it's not a rectangle, probably. It's probably like a parallelogram. Right? So how do we understand that parallelogram? We're going to have to do some careful geometry, blowing things up as we usually do. Here's our little piece of surface. Again, we're going to understand that as the image of this piece of area over here. And we're going to do so by looking at that vector and how it has as its corresponding image a vector like that. And then this vector and how it has as its image a vector something like that. Once I understand this purple vector and this red vector, I can make this parallelogram here's our parallelogram here. That yellow parallelogram is not exactly the same as the actual. Of course, the actual piece of surface is curved, right? But in the same way that this vector here does a good job of approximating this piece of curve, even though the piece of curve is actually a curve, right? Likewise, we expect that this yellow parallelogram is going to help us, at least in approximation, understand that green piece of surface. And in particular, the area of that yellow parallelogram is going to be our approximation of that green area. Okay, so how do we understand this parallelogram? Well, just as we say over here, we're going to understand it sort of one vector at a time. Let's talk about this purple vector. Right, so in other words, if I displace in the u direction by some amount du over here in the domain, that's gonna, this displacement in the domain is gonna cause some sort of a displacement like this in the target. What is that vector? Just like we did in the curve case, we're gonna understand that vector one coordinate at a time. It has an x coordinate that can be understood with derivatives. And then we'll get to the y coordinate in a second. But let's think about the coordinates of this vector. Here's the x coordinate. Right, that x coordinate says, as I move as described, don't forget we're moving in the u direction by an amount du. As I move as described, how much does the x coordinate of the output change? There's that little calculation. Right? This partial derivative says I'm going to hold v constant and move in the u direction, as I am here. And I'm going to move in that direction by an amount du, right? Thus, this factor. And so altogether, that's our formula for how to compute the x component of our purple vector. And then notational convenience, don't forget that little sort of Newtonian notation for partial derivatives, very convenient examples such as this one. So the way we're actually going to write that is as XU du. Okay, analogously, how much does Y change as I move in the U direction by an amount du? Well, the Y partial is going to tell us that. How much does the Z component change as I move in the U direction by an amount du? So, same sort of setup. We're still considering what's happening as we're doing. My elbow again. Sorry. We're still considering, what's going on as I move in the U direction by some amount du, and trying to keep track of how the outputs change, just looking at different output coordinates. So we take U partials of the different output coordinates. And all together, though, notice now that we have all of the coordinates of this purple vector, we know the purple vector. And you can factor out du, common factor of du and all of those coordinates, and all together is you get the parameterization function x. Just take its entire partial derivative with respect to u, multiply by du. There's that formula. We're going to see some examples in a minute. Okay. Alrighty. So, punchline of that calculation is that this vector is computed by that formula. Now, of course, we do next have to figure out what is that vector. That vector just says, suppose I move in the v direction, holding u constant, moving in the v direction by some amount dv, analogous argument, we get xv dv. And I'm going to leave those details as an exercise for y'all to think through on your own. This is a nice practice problem. Again, to make sure you really understand the argument that we just went through in the u direction, digest it, make sure you're comfortable with it, then set it aside, pull out a blank sheet of paper, reproduce that argument in the v direction, make sure that makes sense. Yeah?
If du is on both sides of all those equations, why do you even need it?
What do I need? What?
Why do you need du on both sides of these?
Yeah. So you're asking why I need the du right there. I could cancel it from both sides. Is that what you're saying? Because I'm not interested in the equation. I'm interested in how that's those are two different expressions representing that thing. That's what I'm interested in. This is what I care about. Right? I need to know the coordinate of that vector, and that coordinate is computed by the appropriate partial derivative times the input change. That's what gives me the output change. Yeah. Okay. So good practice problem. Make sure you can justify that vector is that. Okay, so this is the bulk of the work, really, in doing the deriving the formula that we're about to get to. You're writing down this geometry. Now, let me just remind you, knowing that vector and that vector, the whole point of that was that I can use those two edge vectors to help me understand the area of this parallelogram. That area being one of the areas involved, that's the output area that I want to relate back to this input area. I want to be able to understand ds as it relates to, du times dv. How do I compute ds? Well, ds, that's a chapter 12 problem. If we have a couple of vectors in R3, how do you find the area of the corresponding parallelogram? Cross products. Right, you take the one edge vector, the purple vector we computed, the other edge vector, the red vector we computed. The magnitude of the cross product gives me the area of the parallelogram. So again, going way far back to early chapter 12. Yep.
How can you pull du and dv out of the magnitude formula?
How can what?
Can you pull du and dv?
Oh, yeah. In fact, that's exactly the next thing that we're going to do. Yeah. So you got a little ahead of me there, but yeah. So this du here just pulls right out, and this dv just pulls right out, and that's because they're just constants, or scalars, right? So scalars pull right out of cross products, and they pull right out of magnitudes. And so notice we actually then get what we were interested in. We wanted to find output area, ds, that area of that little parallelogram. How does that relate to the input area, du dv? And through this calculation of ds, we see what that stretching factor is. That stretching factor is just what's left over here. This magnitude of xu cross xv. Kind of a weird formula, really. Would have been nice if it had been more sort of crisp and satisfying as just speed, right? Magnitude of the velocity vector. We've got a really nice answer for the stretching factor in this case here, where we were looking at curves, and it's admittedly not quite as convenient or crisp or whatever you want to say as it was in that previous example. Nevertheless, this is what it is, and there's our stretching factor. And now it's all over with the shouting at this point. This double integral, we've pulled back. Let me use the colors, right? We've pulled back from our original domain to our pullback domain. The function is what it is. You just got to plug in for the parameterization, just like every other pullback we've ever done. And the ds is understood by the stretching factor, right? You get this extra factor in there that comes from the pullback. And there's your formula. And it's pretty much plug and chug. And we're gonna plug and chug several here, but anyway, that's the formula to use. Alrighty, now a couple of quick comments before we actually get our hands dirty. Just a notational thing. This vector, as it turns out, this thing here, this xu cross xv, it ends up coming up in future situations. It's not just this one instance. And so this is worth giving a name to because it comes up so often. So the book's choice here is to call it capital N, which I'm going to go ahead and go with because that's fine. There's nothing magic about that, of course. But henceforth, capital N will refer to the cross product of the two partial derivatives of the parameterization of a surface, just like this. All right. So rewriting with that in mind, this stretching factor now looks like this. Keeping in mind that is that. Okay, so that's one comment. The other comment I want to make is about what else you can do with this kind of an argument. We can understand, let's see here, output sizes as they relate to input sizes by way of looking at the output piece, thinking about how it's approximated by vectors, and understanding those vectors one component at a time, looking at partial derivatives. So we did it here to understand the stretching factor for a line integral. How long is that little piece of curve? Then we did it down here. Right, this this purple vector breaks down in coordinates. It's got 3 different coordinates, each of which can be computed with a partial derivative, and then use the appropriate Chapter 12 formula to find the resulting area. And there's another situation where you can take advantage of really the same idea, just a ever so slightly different situation, and that is the change of variables formula. So you might recall when we did change of variables, the stretching factor, I just said, trust me, here's the formula. We'll talk about where that comes from later. Again, the reason I do that is because when we're doing change of variables, there's so much other stuff going on. It's the first time that you see this idea of a pullback and this idea of a stretching factor, and I didn't want to go off into the weeds of the details of how to find that stretching factor. There's enough to keep track of as it is. But if you'd like to know how to derive that formula for the stretching factor in change of variables, it's the same exact argument. It's just a 2-dimensional instead of 3-dimensional. In fact, here's the way you can draw the picture is just kind of erase. Here I said that vector has 3 coordinates. Okay, let's just erase that. And now let's just declare that this vector over here is in 2 dimensions. Right? It now has 2 coordinates. That vector has a first coordinate. Well, that's how you compute it. right? And it has a second coordinate. Well, that's how you compute that. And then think about, once you have these two vectors in 2 dimensions, what is the formula for how to compute the area of a parallelogram in 2 dimensions, not 3? Right? In 2 dimensions, not 3. And y'all remember that formula? And it's a determinant, absolute value of a determinant. And you can kind of see it starting to work out, right? That formula, stretching factor formula for change of variables, the absolute value of the Jacobian determinant, it's going to come straight out of this argument. I think that, too, is a fantastic exercise. I want to encourage everybody to do this on your own. Fill in those blanks. Derive for yourself. It'd be a great test to make sure that you understand what's going on here, right? As we argued this in 3 dimensions for surface integrals. Do the analogous exercise, the analogous calculation to get the stretching factor for 2-dimensional change of variables. And if you have any questions, come to my office hours. Very happy to help. Likewise, the 3-dimensional change of variables, again, totally analogous. Another good exercise. Okay, let's get our hands dirty. So let's suppose that we have a surface S that's parametrized by that function. Now, as with my first example of change of variables, notice I'm making for a sort of an easy starting example where I don't just give you some geometric description of a surface. I'm giving you the surface by giving you the parameterization. Right, so the question of where does the parameterization come from? How will I find the parameterization when it's not given? Yeah, we'll talk about that in a minute. But just to get our hands dirty, first time through, here's the parameterization of our surface S. And notice, implicit in this parameterization, I'm telling you the range of values that traces out S. I'm actually telling you what the pullback domain is in the UV plane. The pullback domain is going to be the rectangle where U is between those values and V is between those values. Okay. All right, so we've got this surface in space parametrized, and what we want to do on that surface is we want to compute the mass. And of course, if you want to compute the mass of something, you have to know the density. So here's the formula for density. How would we use this formula for mass per unit area as a function of position in space? How are we going to use this to compute the mass? Okay, so the first thing to realize is mass is a surface integral of density. Chop it up, add it up. This is just a callback to, if you look at, the big idea of, what is a surface integral? A surface integral is a shorthand for chop it up, add it up. On each little piece here, I want to multiply something, let's say density, let's say mass per unit area. I want to multiply by area to get mass, and then add up over the entire surface. Right? That's exactly what we're doing in this example. Here we are. Okay, so that's why we have a surface integral. Now, in order to be able to evaluate this surface integral, we know we're going to need to know this stretching factor. That stretching factor is the magnitude of our n. You can't compute n without computing these two partial derivatives, xu and xv. So, get to computing is the first step in the process. So notice that's the very first thing I did here. I took this parameterization, x, and I'm taking the partial with respect to u, then the partial with respect to v. That's easy calculus, easy partial derivatives. Okay. Cross product gives me the capital N vector straight out of the formula. That's just chug, right? And the stretching factor then is the magnitude of that capital N vector that we just computed. So, compute. And this punchline is that the stretching factor is 2 square root of 14. It's just a matter of cranking it out. Every time you do one of these, every time you do a surface integral with a pullback, you got to go through this same little song and dance. So partial derivatives, cross product, magnitude. Okay. All right. At this point, it's very much plug and chug. So don't forget that our formula for density was here. There's density. You might wonder, what do you do with the x's and the y's and the z's? How do I turn those into u's, v's, and w's? Well, just like with change of variables, I mean, after all, it is a pullback just like change of variables. How you plug in comes from the parameterization itself. So this x right there in the formula for density, you can see it right there. X is u plus v. That's what the parameterization is telling us. Y is 3u minus v, and z is 2v. That's just plugging in. Right? Is everybody on board? Questions? Everybody happy? The ds, don't forget, how do I understand the area of this, corresponding little curved piece of surface? What is the ds? I can't just rewrite that as du dv. Of course not. You have to include your stretching factor. We computed the stretching factor previously as the magnitude of n. So don't forget to stick in your area stretching factor, lest what you write down be nonsense, right? And we're all done except for direct computing. We've done the pullback. Remember, our domain was given in the statement of the problem. Our pullback domain here is that rectangle indicated by the given range of values for u and v. And now it's just a double integral, and you guys can compute that. Everybody good? It's really a very mechanical process once you have the formula, once you understand where the formula comes from. Okay, so this parameterization that was given in the previous problem won't always be given. How do I find a parameterization? There's not a single method for doing this, but there is a very often good method for doing this. This will very often work. Try to write one of the coordinates in terms of the others. Try to solve for z as a function of x and y. Maybe you solve for y as a function of x and z. Whatever. Try to find one of the coordinates in terms of the others, and then basically go from there. It'll pretty much fall in your lap if you can do that. So, for example, here's a plane. How would I parameterize this plane? It's not given as a parameterization, but can I solve for one of the coordinates in terms of the others? Yes, I can. In fact, I have many such choices. Here I've solved for z as a function of x and y. No particular reason. You don't have to. I don't know, alphabetically or something, it seems kind of more comfortable to maybe solve for z. And all else being equal, maybe, sure, go ahead. But in this case, you could have solved for x if you'd wanted to. Anyway, once you solve for z as a function of x and y, notice that tells you pretty much how to do your parameterization. That tells you what to make z if you just choose to let x and y be your new parameters, u and v. It makes for a really easy punchline there. Let x and y be whatever you want, u and v. Okay? And then, well, if x is u and if y is v, I mean, unavoidably, if x is u and if y is v, then this is what z has got to be. And notice this is a parameterization. We have position as a function of two input variables, u and v. Yeah?
What about the domain?
Oh, that'll depend on the detail. Here I've just parameterized the whole plane. If you have not the entire plane, then you have to think about what else is given, what describes the piece of the plane that you're talking about to be able to figure that out. And it very often comes from context. Yeah. Okay. So, again, what makes this possible, the brilliant choice here is not just to let x be u and y be v. That's an easy choice, but the thing that makes this all come together is the fact that I've solved for one of the variables in terms of the others. That's what allows me to then complete the parameterization. Without having done that, this whole thing crashes and burns. Okay. All right, so keep that in mind. Okay, so some examples. I'm going to go through these examples, skipping a lot of the algebra because you guys can do algebra, right? And time's a factor. I want to focus on the important ideas, the conceptually challenging ideas, where I can be the most use to you. So let's parameterize this hemisphere, the upper unit hemisphere, described by this algebra here. Note we're looking for just the part of, on or above the xy plane, so z greater than or equal to 0. All right. So if I want to parameterize this, I need to, in this algebra here, solve for one of the variables in terms of the others. Now, please do be very careful about this. Don't think too much from a symbolic manipulation point of view. There's a temptation to say, oh, all the variables are playing the same role there because they're all being squared. So I could solve for x, I could solve for y, whatever. Not so in this case. Notice the asymmetry, you might say, is that z is the one that has to be positive. X doesn't, y doesn't. Right? You can see it in the geometry by noticing that this hemisphere, right in the geometry, you can see that you can't solve for y because for any given values of x and z, there are two different values of y. Right? This fails the what you might want to call the vertical line test in the y direction. Right? Y is not a function of x and z. Likewise, x is not a function of y and z. Fails the vertical line test in that direction as well. But it passes with flying colors the vertical line test in the z direction. For every vertical line, there's exactly one intersection. Okay. All right, so we solve for z in terms of the others. Easy algebra. There you go. And notice, just like we did on the previous case, we let x be u. Keep in mind, this is our parameterization, x, y, z. So we are letting x be u, y be v, and then, as we must, z is square root of 1 minus u squared minus v squared. All right, everybody happy? Now, to the question that came from a few minutes ago, what does that mean about the range of values of u and v? What is the range of values of u and v? Well, you can see that from the picture in this case. So our hemisphere is like this, and notice for every point on the hemisphere, right, the corresponding values of u and v, well, let's see here. That point from the parameterization comes from these values of u and v, which are, namely, they are just the x coordinate and the y coordinate of that point. They just come from straight down below that point. So u and v range over the same values that x and y range over, namely, u and v range over the projection of this surface down into the xy plane, or said differently, from the unit disk in the UV plane. Everybody on board with that? Okay. All right. All right, now I'm going to show you another way to parameterize this same upper unit hemisphere. This is different. You're not going to like it first time you look at it. This is going to seem unnecessarily complicated. It turns out that this is actually really, really convenient. This is your friend, not your enemy. You will learn to like the following seemingly awkward choice, and that is to use spherical coordinates. All right. So, in fact, let me zoom out where I can get all this on the page here. Take the point of view of this upper unit hemisphere as being described by this algebra instead of that algebra. So just ignore the rectangular coordinates. Sphere, radius 1, is easy. In spherical coordinates, it's just rho equals 1. Now, what do you do? How do you turn this into a parameterization? You can't just let x equal u, y equal v. Yeah, that's not sort of what we're doing here. There's no x. We're not really... Anyway, what's different is you just have to stick in the formula for spherical coordinates. That's how you compute x, y, and z in spherical coordinates, right? And into that, plug in the variable that you have solved for in terms of the others. Okay, so rho equals 1, so stick that in there. So that's a 1, that's a 1, that's a 1. And notice, not unlike what happened when we did this in rectangular coordinates, out comes position as a function of, here, let me do it like this, position as a function of two input variables. That's phi and theta instead of u and v, but there's nothing magic about u and v. Phi and theta work just as well. So what we have here is a parameterization from the phi theta plane instead of the uv plane. The math is all the same. Okay, what's the range of values here? And again, we're looking at this hemisphere. And you just got to think, back to spherical coordinates. How do you find the range of values? We just think about what do phi and theta do, and how do they vary. Theta, there's a theta cross section, right? That's where theta is equal to 0. And I think I can persuade you without too much trouble that theta goes from 0 to 2 pi. Yeah, and then for any given value of theta, for any given value of theta, such as that one, phi starts at 0 and ends at pi over 2. So you can see here, theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2. Our pullback domain is this rectangle. Now, let's compare. Which one of these do you like better? And first time I saw this, I thought, you know what? I see a lot of trig in there, and that trig is kind of a little scary to look at. I'll go ahead and take this one innocent little square root. Thank you very much. Right? And it seems like that would be the better way to do it. And it's not. We're going to see on the next page why it is that the spherical parameterization is so much more convenient. It comes from how would you then use these parameterizations. So we've got two different choices of parameterizations for the sphere. How would you use these to actually do a pullback? So here we go. Let's. I guess I'll go ahead and zoom in on this. Might as well. So suppose you want to compute, let's say, the area. Area, of course, is just integral ds. Density is 1, if you like. How would I do the pullback? Well, we know we have to take the partials, and then you have to take a cross product, and then you have to take a magnitude. And notice that the algebra gets a little hairy in there. In fact, and the algebra of square roots is kind of annoying. Right? You don't have a lot of friends in your algebra of square roots. You can factor stuff in, factor stuff out. That's kind of about it. And then furthermore, notice that your resulting stretching factor, right, that you have to include. Remember, when you rewrite ds, you got to stick in the stretching factor. That stretching factor makes this integral pretty undesirable. Furthermore, notice u and v range over a disk which is pretty undesirable as a domain. Square roots. So there's square roots all over the place here. Now, I admit polar coordinates would be a great choice here, and that will help things quite a bit. But look how easy it becomes alternatively if you use spherical coordinates. Sure, you take the partials. Sure, you take a cross product. And then you compute the magnitude. Same process. And yeah, there's a fair amount of trig. But in this process of going through and computing that stretching factor, you have a lot of algebraic friends. Trig identities. right? And so it's not that you start off with a certain amount of trig and then through derivatives and cross products and magnitudes that the expression gets increasingly big and ugly. That's what you're kind of afraid of, right? This is not what happens. It gets really simple, really nice, because the Pythagorean trig identities just kick in all over the place in that calculation. It's a wonderful little calculation. Everyone should do this once in their lives, right? And look how easy the resulting integral is. You can do that in your head, right? Constant bounds, easy antiderivatives. Super nice. A lot of y'all are engineers. Again, engineering not that different from the physics major that I did as my second major. I did a bazillion integrals. By the way, the world is full of spheres. And physics is about, very often, those spheres. So I hope it comes as no surprise. In my physics major, I did a ton of integrals on spheres. I can tell you, that's the way to go. This is definitely the easier way to do those kinds of integrals, vast majority of the time. Okay. All right. All right. Now here's another version of the formulas that we've just been talking about. I want to remind you our primary formula, primary pullback formula for a surface integral is this formula right there, and you can see your formula for your stretching factor, and we know how to compute this in thing. In is that, and blah blah blah. Okay. If, this is a big if you are using a parameterization that comes like this, where you solve for z as a function of x and y, where you then correspondingly use that to make your parameterization, this is what I call the rectangular graph parameterization, where we're viewing the surface as a graph, and we're capitalizing on the fact that it is a graph in rectangular coordinates to create our parameterization. So if you are using this rectangular graph parameterization, the stretching factor formula does simplify pretty nicely. So here's our situation. If we are choosing to view x as u, y as v, and then z is, whatever it is, if that's your parameterization, well, then the partials up here work out really nicely. You can write down what these vectors are. You can take that cross product, you can write down its magnitude, and here it is. And it's always that. So this is a good formula to memorize. I encourage you to memorize this formula. I emphasize this is not an alternative to the previous formula, because this is a special case. This works only if you are using the rectangular graph parameterization. If you're using a spherical deal, this does not work. This is wrong. It's big time wrong, right? And if you're using a different kind of a parameterization, of course we have lots of different kinds of parameterization, then this is big time wrong, right? So this is a special case formula. However, it's a common special case. In that special case, it is really convenient. Then in this special case, you can rewrite. Your ds is your stretching factor, times du dv, which you can write as dx dy because x is u, y is v. The book does it that way anyway. And I see that I forgot to include my delta in here for density. Sorry, typo. So again, nice special case to keep in mind. Definitely want to memorize it. Do not rely though on this formula. Okay. Alrighty. Okay, so we're going to move on now to Chapter 15. A quick reminder, the stuff that we're talking about today is not fair game for the midterm exam. I sent the email with all the official fair game material enumerated. But this course being as full as it is, we don't have time to do, spend an entire Monday before the exam doing review. So we press on with new material, weirdly, even though it's not fair game for the exam coming up. So anyway, so I am going to press on. We're going to spend a little bit of time talking about one of the big objects in Chapter 15 is something called a vector field. This is a new kind of mathematical construction that we haven't seen before. It is something that associates to every point in space a corresponding vector like that. So at every location in Rn, there is a corresponding vector sitting there, you might say, in Rn. Now, why would we do such a thing? We're going to spend some time talking about this, but you could imagine, for example, that maybe this represents the flow of a fluid. You can almost see the fluid flowing, right? Something like that. Right? It might represent forces or something. Wherever you are, here's how the magnetic forces or electric forces or gravitational forces act on you at that point. Something along those lines. So we'll spend a little bit more time talking about those applications, real world instances. But first, I just want to talk about these as a mathematical object. So a vector field it just means that at every location in the domain, you associate a corresponding vector. All right. Note you can think of this as a function because for every point, the point is a element of the domain Rn, and then there's a corresponding output, which is the corresponding vector, but of course that is a vector in Rn. Right? So you can think of this as a function from Rn to Rn. Critically, the domain is playing a conceptually very different role from the target. Even though the domain is Rn, the target is Rn. It's Rn to Rn, and it kind of feels like, well, the domain and the target is the same thing. You're thinking of the points in the domain as being locations, points, places. You're thinking of the outputs in the target as being vectors, right, that we represent with arrows. You're thinking of them as directions and magnitudes. You're not thinking of the outputs as being places. Okay. All right, a quick example. Here is a vector field. For any given input point, there is a corresponding output vector. You compute it like so. So just to, again, get our hands a little bit dirty, if you look at the point x equals 1, 2, there it is. There's that place, location 1, 2. At that point, well, you plug in x equals 1, y equals 2, and compute. And out comes 0, 2, thought of as an arrow. And I just plugged in that single point 1, 2, but obviously you can do this at various other points, and I couldn't tell you exactly what this is going to look like, but at different points you're going to have different corresponding arrows, something like that maybe. Okay. All right. So very importantly, recall I'm real big on this idea of not conflating terminology. So I want to emphasize these are not graphs. The pictures that we're looking at here, these are not graphs of those vector fields. We can't draw a graph of a vector field. We don't have enough dimensions, not even close. Right? A vector field in R2 is a function with 2 input variables and 2 output variables all together making 4 variables. I can't draw 4-dimensional pictures. So these are not graphs. These are not level sets. We're not parametrizing anything. This is a new kind of picture that we have to come up with a completely new kind of, how do you think about calculus in the context of these pictures? And I guess that makes for a good stopping point. We'll pick up here on Friday. So final reminder, exam Wednesday. See y'all then, and good luck to everybody.